Okay, dear colleagues, we will start our first seminar in this year, the talk by Sergey Khoroshkin from BIMSA and High School of Economics, yes? Okay, right. Let us start.
Actually, it's not, I will talk about the subject which was already in the seminar. Nikita Belosov talked about this once, so maybe not so much new will be today. And I will talk about the Ruijsenaars hyperbolic system, properties of eigenfunctions, and the related spectral transform. So recall that Hamiltonian, the first Hamiltonian by Ruijsenaars and MacDonald, it can be written as a sum of coefficients applied to the function, then it will be the function of I so this difference operator included into a family of computing operator which looks similar. It has three parameters, omega 1, omega 2 periods, and G is a coupling constant. And this Hamiltonian has degenerations. One degeneration is when we tend omega 1 to 0 and put the product to be constant, that would be G bar. Then this Hamiltonian generates to hyperbolic Sutherland, which is Laplacian. This functions of this is one degeneration, well known. Another degeneration is when contrary omega 2 tends to infinity. Omega 1 we take fixed to be p pi, so also fixed, and it tends to rational Ruijsenaars-MacDonald, which again we apply to the function. It will be this product sign hyperbolic disappear. And here will be again the shift of the variable to imaginary direction. Sorry, it should be 1. Should be 1. Maybe right. And in this system, what are the main players in this game? First of all, there is a double sign function, which can be characterized by two functional equations. The first one, another one. This function is known by many others' name, like hyperbolic gamma function, merely inverse to this, hyperbolic gamma, or slightly different, but the same. It's relative to quantum logarithm by Faddeev, and many others name probably because many people discovered this function by themselves. And from this function, we have maybe two main, not precisely this function in use, but some of them of its composition. So first of all, this function k of z, which is I now do not write this index 2 because it's always assumed. This may be called by as Ruijsenaars. Kernel and another combination is this way here. G star is maybe written here. G star is a dual coupling constant. In the translation in the limits, in this limits, differential k of z, it tends to cosine to the power g, mu tends to sine hyperbolic z, and in rational limit, k of z is gamma. In rational limit, in both limits here, g star is 1 minus g just. So it will be again and mu of z is gamma over 2 multiplied by minus z plus z star. And from these functions, where here minus, it doesn't matter. I can put. You see further that they comment in the product, so I can put here plus or minus, it doesn't matter actually. So here is difference to s minus 1. Here both are inverse gamma function. And both of them come into the product. We have now many variables. So the k of x1, xn, y1, ym, and it is a product of k of xi minus, and it is usually called as Ruijsenaars kernel function. Its place can be considered as an hyperbolic analog of reproducing kernel in McDonald's theory. And we have of one set of variables. It will be product mu xi minus xj. This will be measure function. Okay. So from this, ingredients, one can construct the wave functions. So the formula for them looks rather simple. This is a function of n spectral variables and n spatial variables, which can be defined recursively in the following manner. Here, lambda prime is a set of variables without one as the last variable. So you see that the wave function in n variables can be defined via the function of n minus 1 variables by integral operator, which is an integral operator with respect to measure. This is measure defined by this function. So, and the kernel is this one. So in general, you see, repeating this procedure, we obtain the formula as integration over n minus 1 over 2 integrals. And what is can be immediately shown, it's actually not so difficult that the Hamiltonian when it acts on this function. It gives the eigenvalue which is the first elementary function of this exponent. The next Hamiltonian will give next elementary function of this exponent as eigenvalues. And to closely related to this formula, you see in this formula, if you look carefully, this function k depends on n variable x and n minus 1 variable y. But if we can write down similar formula with equal numbers of variables, and we get the definition of Baxter Q operator. Lambda? No. Everything are continuous variables. It's hyperbolic theory. It has continuous spectrum. So it's not McDonald polynomial. It's other side of story. So Baxter Q operator, Q of lambda, depends on the parameter lambda. Once we apply it to the function, it is, of course, here is some constant which I do not write here, and here is also the same constant. It will be integral. So dependence of lambda comes only here in the exponent. It will be k of x, y, mu of y, f of y. So this is just integral operator with this kernel, integration again with respect to this measure. No, it's not. So you mean the point of free fermion point here for g equal to 1? It depends on. So it's in a differential version of this. But you see, the definition is universal. So you substitute, if you want this Q operator in Sutherland theory, you do the same, but instead of K, you substitute its meaning, and you get the definition of this operator. And the eigenfunction, yes, there will be some of them will be sure function of exponential, so like a combination of free waves. Yeah.
Not polynomial, it's functions. That's the difference. It's different branch.
Yeah, there are no polynomials. So you see what, for instance, yeah, in hyperbolic case, for instance, for n equal to, you get for McDonald's theory, you get polynomials, sure polynomials of two variables. here you have Bessel function, or some which in this point they degenerate to trigonometric function. You see. That's it. Okay, let's go further. Correct, yes. Yes, it happens precisely in for special coupling constant g equal 1 or 2, but in differential case. And this will be the integral which you can calculate and get an answer as a determinant here. Yes, that's right. It's not no, it's some requires some work. It's not not immediate, of course. It's a calculation of better integrals. Okay, and what is good in this situation that this Q operator written this formula, they commute between themselves. And they also commute with Hamiltonian. This is easy, and this is difficult. Actually, this equality is certain integral identity which cannot be even obtained from known integral identity by Rhines, and it's a little bit different. It's everything because of the measure. You see, in the measure, you have this point, and in all integrals, in known all integral, the gamma function denominator in multidimensional case do not contain the part like this. Thus, it's. But then, if it's so, then okay, the wave function. So sorry, to Q of lambda. Yes, it is. When you apply it to the wave function, since they commute, but again, the wave function, and what is the eigenvalue? And the eigenvalue is the product and what is this? And this here first we see the trace of duality. So this check means so you take the same function, okay, but you change this function depends on the periods. You change the periods, and you change the coupling constant. In a simple case, of course, if which physical, which is usually used in the physical literature, omega 1, omega 2 is equal to 1, and omega 1 is b, omega 2 is 1 over b, and then you can assume that omega unchanged because everything is symmetric actually about with respect to this omega 1 and the check is, but more correct point of view in this one, and even you can speculate somehow that one of omega is like a Planck's constant, another like a velocity of the light, and they interchange to each other, but it doesn't matter. But now if you look to this formula, what you see that another Q, you can produce, you see here another kernel function, and this is the reflection of the spectral duality. Which means that may be formulated in different way. First way, that we have another integral presentation for the wave function. Which is given by some constant again, prime, which is given by integration over spectral variables. And also you have checked Hamiltonian, which is given by the same formula as Ruijsenaars Hamiltonian, but they act on spectral variables, and with all this data, which is written. So and the eigenfunction is again the eigenfunction of this apparatus. So it will be sum of J with the same eigenvalues. And what else? And you have, of course, dual Q operator, which act on function of lambda, which is given by analogous formula. Integration of n variables x or in usually maybe written in this way, that we have a symmetry. If here we have omega g, and this is the same as psi x of lambda, but with different data. If we look to what does it mean for the generation, you see that for Sutherland model, we have actually expression of the wave function first as beta integral, usual Euler integral, and here will be product of sine to the power g divided by product of cosine and the same is given by Barnes integral. Here will be the previous function. Here will be the product of gamma plus minus I divided by gamma of plus minus I gamma I minus gamma j. Psi gamma of x prime b gamma. And so there will be precise equality of this expression. In Macdonald theory, this duality is written usually as equality of normalized Macdonald polynomials. Where lambda of x of z is lambda of z divided by rho as usual is to change lambda. So here we have this equality. Yes. Yes, it's right. It's I do not touch elliptic. It's so in trigonometric case there are Macdonald polynomial precisely. So if no, see, the differences you see here is a duality in Macdonald polynomial. Here is duality for Ruijsenaars function. So in a sense they're similar, but so it's like you see for Macdonald polynomial, it's you have decomposition of function in Fourier series. It's like in Mondolin theory. And here is like Fourier integral. So this. Okay. But now you see in all this story that in all the integrals, there appears special case in the measure, the shifted gamma functions, the shifted double sign functions, which prevent to calculate the integral precisely. And this is not occasional. This division plays important role, actually. So let me introduce special notation for this. So I divide this function, measure function, into two, which is delta of x multiplied by eta of x, where delta is will be the product maybe in this way, as 2 of plus minus I, a minus 3. It's like a Vandermonde. It's and if you write down delta of x dx, this is usual. It is usually called Sklenin measure. But we have another here, eta of x. What is it? It will be product of s of I minus xj plus g star. And this function eta appears from the very beginning, namely what it's more or less we have the property. It depends on the constant g. And first of all, one can note from the property of this function that if we take dual constant, then this function will be inverse to this one. And what is also known in Macdonald's theory and here, that the Hamiltonians for G and G star, dual constant are related, are conjugated. Namely, we have the following relation. That Hamiltonian x with respect to m1 of x, so here will be omega g star is equal to, one can see precisely formula. So this function eta, it connect to Hamiltonians with the constant g and constant g star, which may, so we see that from this, the wave function of Hamiltonian with dual coupling constant should be simply related to each other. But more interesting is that from this equality, we have another duality. It is like coupling constant G star duality, which can be formulated as follows: that psi lambda of x G omega and G star is equal to eta of x, eta check of lambda multiplied by the wave function of x omega g. This relation already cannot be observed in a classical case because in this case we have no good limit of this duality in this to classical case, and this how to prove this. The proof of this duality is actually based on Rhine's integral, so namely on this an Rhine's integral identity. More or less, it is equivalent to this. What is identity? Maybe I even can write it down to see how it looks. So, for special parameters which we need here for the integration, this can be written as follows: as we have eta of z will be over imaginary So this integral equal to the same integral with replacement g and g star. So we have, you see, two types of duality as usually predicted in Ruijsenaars theory, but they are formulated in a quite precise way. And now what we want to do further of course, one can assume, if everything is good, that there are relations of orthogonality relations. The theory is that these functions, wave functions, form a complete orthogonal system. But such a formulation is possible also if this theory is unitary. And there are actually 4 cases of unitarity. Namely, the first case, which is most studied, is when everything is real. And the constant is between and all the game is going in this strip. But there is another case which is similar to this, when they are conjugated and G again real, and again G or real omega 1 plus 2, the same. From this theory, we can to Sutherland's theory, and this one, when both omega tends to imaginary line, this comes to how it's called, it's complex complex Sutherland, where all the gamma function are replaced by a gamma function over for complex field, which it is the theory well developed by Spiridonov and what else, I do not know, Neretin, and so on. And but there are also 2 more cases, namely this third case when the periods are real again, but G is not real. Satisfy this equality, which means that G is equal to omega 1 plus omega 2 over 2 plus imaginary part. This means that the coupling constant now is here. So the first case is this coupling constant in the interval. Here is on a vertical line. And fourth, the same like here, omega 1 equal to omega 2 conjugated, and G is again so the third case, it appeared in recent work which with Shapiro and Guth-Schroeder, where there was attempt to relate McDonald's theory with Whittaker theory, so to obtain this function from Whittaker wave function, and the operator which transform one to another, it image is precisely in for this constant. So this were expected. So how many time I have? This. Okay. And to formulate what's going on, I need to introduce, to say, so this is orthogonality relations for which form, actually. And in this game, we have actually two different objects. First of all, there is a bilinear form. It's on the space of spatial parameters is the same, maybe phi and psi hat. Hat, yes, again will be minus lambda, z of lambda, lambda, lambda. And we have, of course, usual Hermitian forms. And if you are familiar with McDonald book, so in McDonald book, there is analog of this one. It's called second scalar product. Which is fg equal to integral over model z equal to 1, z minus 1, c. Here is delta z dz. So which means that in McDonald's theory, Hermitian product are never used. Or the product is used is bilinear. And actually the same story is here. To prove all the theorem, to prove orthogonality, actually all the proofs are going with these bilinear forms. But in the case of unitarity, we have the equality of scalar product. This is for G real. This is because in this case, it's the same. And there is another product. So if G star equal to complex conjugated to G, then there is equality that is lambda of x. So, mu of x mu is equal to scalar product so you see bilinear form on the wave function in this regime so coincide with scalar product but with Kleinian measure. Therefore, all theories are related. Of course, one should expect that we have something like this, that the scalar product, for instance, like the equality of psi lambda of x, equal 1 over the hat of lambda so this is different, but actually in the same dual space symmetrize x minus y. It is expected, but actually what is true that we should understand this equality in more accurate way. First of all, it is correct with scalar product bilinear form, but if you want to write down to understand what does it mean, then you should understand. So this is an equality in distributions, and you say precisely what's the distribution you mean here. And for this case, so there are two meanings of these equalities. So the first meaning that spectral transform send f of x to f of lambda, which is scalar product of psi lambda of x f of x. This is extends to isomorphism of L2 spaces, but it's because everything is done for complex scalar product. Actually, more serious statements are valid, namely the second, that if you defined analog for an analog Schwarz space, which consists of the function which are first phi of x analytical in the strip in xi less than real part of omega 1 over 2, real part of omega 2 over 2, minimum of this, and fast decrease with a precise bound. I do not write in here because I have no time. Then we have the inversion formula. So it means that for complex parameters, not real, not specially real, in this Ruijsenaars theory, spectral transform behaves as Laplace transform. So we can formulate the inversion theory here. So we can restore actually the function from from a spectral transform. So this is more or less what I want to say about. Thank you.
Okay. Any comments? Any questions? Okay. Okay. Let us thank our speaker again. Thank you very much. So the next speaker, Anton. After a week, yes, of course. Okay. Thank you very much for all.